Hello, my dear friends. What's up? So, today we are here to discuss the most important formulas of a very important topic, that is electrostatics. Here we have a collection of most important 25 formulas with help of which you can solve any problem related to this topic very easily. So, without wasting time, let us start very quickly. Electrostatics. First comes Coulomb's force between two point charges. F will be equal to 1 upon 4 pi epsilon naught q1 q2 by r square. q1 q2 are 2 point charges, so the force will be equal to, if both are positive then they will repel each other, if they are both negative then they also repel each other, but if one is positive and one is negative then they will attract each other with force equal to this 1 upon 4 pi epsilon naught q1 q2 by r square. Okay. Then electric field intensity at any point E is equal to force upon charge Q, as the electric field is the force experienced by unit positive charge. Next, electric force on a point charge. So force will be equal to Q multiplied by electric field. Then electric potential is the work required to bring unit positive charge from infinity to that particular point in an electric field against the electrostatic force. So if there is an electric field and we want to bring a point charge Q here inside this electric field from infinity, then obviously we will have to work against this electrostatic force, that will be QE. So the work done by external agent to bring positive charge, unit positive charge to that particular point will decide the potential of that particular point. Hope you got it. Now potential difference. Obviously, if the potential at point A is VA and there is a point B where potential is VB, then the potential difference will be VB minus VA or VA minus VB. Then some of the important formulas of electric field and potential. First, due to point charge, here if this is a point charge, then electric field, this is a point charge plus Q, then electric field at point P, that is at distance r, will be given by kq by magnitude of r square r cap. This is the point P, this is charge Q, so this will be the position vector r and this will be the value E. We can also write it as kq by rq into vector r. Then potential will be kq by r. Next, infinite line charge, electric field will be equal to this lambda upon 2 pi epsilon naught r, we can say, 2k lambda by r cap, where lambda is the linear charge density. This is a infinite line charge minus infinity to plus infinity. Here there is a point P at a distance r. So electric field can be given by this. Here potential B is not defined. Why? As we know, potential is the work done by external agent to bring unit positive charge from infinity to that point. But this is also from minus infinity to plus infinity. So V cannot be defined here. Now, but if we bring a point charge from A to B, then that will be there will be a work done to bring charge from point A to point B. And if this is a unit positive charge, then delta VAB will be equal to VB, potential at this point minus potential at this point, VB minus VA. So potential is not defined, but potential difference will be given by this formula, that is minus 2k lambda. Lambda is linear charge density, ln RB upon RA. RB and RA are distance from this line, infinite line charge, and this is RB, this is RA. Distance of A and B from this infinite line charge are RA and RB respectively. Now, infinite non-conducting thin sheet electric field will be sigma upon 2 epsilon naught. Here we have non-conducting thin sheet, that is infinite. So here sigma is this is the surface charge density. Here this is sigma. So electric field at any point P nearby this will be equal to sigma upon 2 epsilon naught. Again, infinite charge, infinite non-conducting. So for infinite, V is not defined, we already know. But the potential difference can be given by here this formula. Now, if there is a uniformly charged ring, this is a ring, this is a ring that is charged uniformly, then electric field at the axis, here this is the axis passing through the center. So if there is any point X from the center, then the electric field at this point can be given by this formula. E axis will be equal to KQX. Q is the net charge on the ring, X is the distance of that particular point on the axis from the center, R is the radius of ring, X we know already. What will be the E center? E center will be 0. By symmetry, this will be 0. For uniformly charged ring at the center, electric field will be 0. Now v axis potential again at this point P will be given by this formula kq under root r square plus x square. Q is the net charge, r is the radius, x is the distance of the point from the center. Then potential v center is equal to kq by r. This is the potential at C. Electric field was 0 but potential is kq by r. Now we have infinitely large charged conducting sheet. This will be electric field nearby this sheet will be sigma upon epsilon naught. See, for non-conducting it was sigma upon 2 epsilon naught, but here it is sigma upon epsilon naught. While charge density sigma is same, so what is the difference between conducting and non-conducting? See, non-conducting is a single layer of this charge with charge density sigma, but for conducting sheet, you know, if this is a conducting sheet, then charge will be redistributed on both surfaces. Here this side, here this side. So this side will give sigma by 2 epsilon naught, and this side will also give sigma by 2 epsilon naught. So after addition, this will become 2 times this non-conducting. This will help you to remember and relate these two formulas. Now potential difference VAB will be minus sigma epsilon by epsilon naught RB minus RA. Here this is the formula. Next, uniformly charged hollow conducting or non-conducting. If a sphere is hollow, then it may be conducting or non-conducting, but if it is the conducting, then this is the formula for solid conducting and hollow conducting as well as non-conducting. So this will be applicable in all the 3 cases: hollow conducting, hollow non-conducting, solid conducting sphere. This is the sphere. Here we have a point at distance small r, that is smaller than radius r. So electric field will be equal to kq by magnitude of r square. Okay, and potential will be kq by r, where q is the net charge on this sphere, r is the distance, small r is the distance of point from center. Next, if r is less than, this was the case for this r greater than or equal to r. Here it was greater than or equal to r, that is point this P. And if r is less than radius, here this r is smaller than radius r, then electric field inside sphere will be 0. This will be 0, while the potential will be equal to the potential at surface. If here we put small r is equal to capital R, that is radius, then we will find the value of this. So potential at surface and at any point inside the sphere in all the three cases will be equal to same this. It will only vary with r if r is greater than capital R, that is bigger than radius. Next, uniformly charged solid non-conducting sphere. So after this we are left with uniformly charged solid non-conducting sphere or non-conducting sphere. If r is greater than r, equal to r, then this will be the formula for electric field kqy magnitude of r square, and this will be the formula for potential kqy r. But if r is less than radius, then electric field will be this kqy r cube. R is the position vector, this position vector. Now this is a solid non-conducting sphere. R is less than r, then this is the position vector r. So the value of E will be kq/r cube position vector r, that can be given rho r by 3 epsilon naught, where rho is the volume charge density. So V can be given this rho upon 6 epsilon naught 3r square, r is radius, minus r, this is the distance of point from center, small r. Next, thin uniformly charged disk, where sigma is the surface charge density of this uniformly charged disk. So E, electric field at any point on the axis of this disk passing through center at a distance x from center will be given by sigma by 2 epsilon naught 1 minus x by under root r square plus x square. And V, potential at this point P, will be given by sigma by 2 epsilon naught under root r square plus x square minus x. So I hope you got it, there is no issue here. Next, we have work done by an external agent taking a charge q from point A to point B. Obviously q into potential difference delta V, that will be potential at point B minus potential at point A multiplied with charge q. As VB minus VA is the work done to bring unit positive charge from B to A. So for charge q, it will be multiplied with q. Now electrostatic potential energy of a point charge U will be equal to q times potential, obviously. So electric energy density, this is given by half epsilon naught E square, where E is the magnitude of electric field at that point. So electrical energy density at that point will be given by half silent knot E square. Then self energy of uniformly charged cell. This can be given by U self energy will be equal to K Q square by 2R, where R is the radius of cell, R say hollow sphere, and Q is the total charge on that cell, or say hollow sphere you can say. So self energy can be given by kq square by 2r. Now this was again the case similar to this uniformly charged hollow conducting, non-conducting, solid conducting sphere. Now we are left with solid non-conducting sphere. So the self energy here will be U self will be given by 3 by 5 kq square by r. Again r is the radius, q is the net charge. So the self energy will be 3 by 5 kq square by 5r. Now electric dipole. Electric dipole is a combination of two equal and opposite charges placed at a distance 2l. So the electric dipole moment P can be given by magnitude of P can be given by Q into 2l. 2l is the distance between these point charges, and its direction will be in the same direction from Q2 minus Q2 plus Q. Direction will be parallel to line joining minus Q2 plus Q. So this is a vector quantity, electrical dipole moment. Electric field due to dipole can be given by E 2k P by RQ on the axis. If here there is a point on the axis and this is the distance r, then this formula will be applicable. On equatorial, this is a equatorial axis that is perpendicular to this electric dipole. So if here is a point on equatorial, then this will be the formula minus kp by rq. Now let us have general formula for the electric field due to electric dipole. See, here there is a point O that is at a distance of r and making angle theta with the axis of electric dipole. This is the axis of electric dipole and this is position vector r making angle theta. This is the theta. Then electric field at any general point O r theta will be given by this kp by rq, the root 1 plus 3 cos square theta. Now see, for this axis theta will be equal to 0. So if we will put theta is equal to 0, then this will become cos 0 will be 1, 3 plus 1 2. So 2 kp by rq, here it is given 2 kp by rq. For equatorial position, theta will become 90 degree, and if we put cos theta is equal to 90 degree, then cos theta will be 0. So this value will become Kp by r cube. This. So better to remember this rather than these two. Now potential energy of an electric dipole in an external electric field can be given by U minus vector P dot vector E, where P is the electric dipole moment and E is the electric field at that particular point. Next, electric dipole in uniform electric field. Now here we given uniform electric field where electric dipole is placed here, let's say at angle theta or something. So the force will be zero. How? See, electric dipole is consist of minus q and plus q. So if electric field, if electrostatic force on plus q will be in this side, then the same magnitude will be applicable for minus q but opposite side. So after addition both will be cancel out, so F will become 0. Equal magnitude but opposite direction due to opposite charge. Now what will be the torque? So torque will be equal to vector P cross vector E, that is electric dipole moment cross electric field. Okay. So obviously if dipole is perpendicular to electric field, then this magnitude of this will be PE, and if it is in the same direction of E, then torque will be 0. If P is perpendicular to E, then torque will be PE, and if P is parallel to E, then P cross E will become 0. Hope you got it. Electric dipole in a non-uniform electric field, that can be again given by tau vector P cross vector E. This is potential energy minus P dot E. Net force can be given by magnitude of net force can be given by magnitude of P del E by del R. Next, electric potential due to dipole at general point can be given by this P cos theta by 4 pi epsilon naught r square. This was our general point O at distance r, making angle theta, position vector is making angle theta, so this will be the potential in this case, P cos theta upon 4 pi epsilon naught r square. That can also be written as vector P dot vector r, that is the position vector, this is magnetic, sorry, electric dipole moment upon 4 pi epsilon naught r cube. Then Gauss's law, what it say? Electric flux passing through any enclosed surface E dot ds closed closed in the integral E dot ds, that is the total electric flux passing through any closed surface, will be equal to Q inside total Q inside this closed surface divided by epsilon naught. This is very helpful. We will see its application in next videos. Now electric pressure at a surface of conductor. If sigma is the surface charge density, then the electric pressure can be given by P is equal to sigma square upon 2 epsilon naught. So these were very important formulas of electrostatics, and this is the most important collection of 25 formulas. You must be familiar of all these cases and also mug up to solve any problem related to this the very important topic very quickly. So this was the purpose of this video, to discuss the most important 25 formulas of electrostatics. So I hope you enjoyed the discussion. Thank you.